I'll be honest with you. Hi there, everyone. Hi. It's day 606. I'll be honest with you all. My last video isn't performing all that well. And so I kind of can't sleep. Or like, focus on anything else much. So I thought I would start today's live stream a bit early. A bit much early. Simply because, as I mentioned, it's not that I'm freaking out. Well, I am, but it doesn't matter. The point that I'm trying to make is, I have a whole video we can work on, and I just feel like, I just couldn't help but feel like since the last video, no one seems to really care much for it, I thought I could just make another one right away, and maybe then people will like it actually. I'm not freaking out. I'm fine. I just need to, it's fine. Yeah. So far, I've rendered everything. We're on the third page of the 15-page document, even though it's not fully scripted, so I will have to script some more, but it's fine. We're on the third page, and I'm just gonna have another sip of coffee. Okay, start a simple mathematical tool. If there's a specific case where there's low potential with the plant, but separated for creating different rules, there's going back to the rectangle example, if we freeze one. Okay, so right here we're gonna need the rectangle. Okay, lovely. It's great, it's fine, I'm fine, and... Oh, whoops, that's the wrong animation. That's the wrong blender. There we go. So right here what we're gonna need is the original rectangle to drop it in. To pop the original rectangle in, alright, so that's gonna be... No, that's my hope posting meme. Aha! I'm funny. Inverse, yeah, and was the multiplication. Alright. So right here, we have this rectangle, which is called a cube, but it's a rectangle. And basically, we can move it right here. In fact, we'll move it right here and make it 90. And then we're going to put it actually on the ground. I feel like that'll be much better. And also, it has the wrong color. Each one of these scenes I would like to have a different color. And so this one currently has a color of... this is not gonna fix it. Right here, okay. Geometry notes this is currently odd color 2, which in fact should be color bright, like this. And then this is going to slowly transition to the rectangle, okay. And then you are going to transition to equal view. So it's just more top down actually. Just call it. There we go. Sweet. And now we can. Well, not quite. Make it 90, and isn't that just straight up fun and festive? The fact that everything is a bit off center is really upsetting me. Okay, so right here you could point somewhere down like this, and we could start with it being just a bit bigger, you know, like 5.2 and 2.4. Alright, then clear keyframes. There we go. And just render. Sweet, nice, neat, festive, fantastic, lovely. So, oh my, last person responding, there we go. There we go. Increase the side, decrease the side. But now I'm imagining the side log and change it. Okay, so this will be simple enough. Each frame takes 40 minutes, which means that's a little bit under half an hour. It's fine, though. We can just work on the complex sign definition of the Eolus identity. Oh right, I forgot. That's the one. I thought we could go with the definition with the derivative, not the proof, the derivative proof for the explanation, because there is a lot of like, I don't want to say coincidences because they're not coincidences, but a lot of things which nicely tie in together to Euler's identity. So I unfortunately won't talk about them. I'll just talk about the proof. Where's the proof? Yeah, the mathematical beauty. Oh no, it wasn't Euler's identity, it was Euler's formula. There we go, Euler's formula. That's what we're looking for. Euler's formula with... Oh, Euler's formula, sorry. Okay. And Euler's formula, and right here formula identity about all of the lovely ways i.e. imaginary numbers. Actually, maybe I will go into it. No, I can't go into it. It would be too long. Ah. Imaginary numbers and so on. But basic idea looks like this. Oh boy. Ha ha ha. Ha ha he he ha. So, should I go with the... Well, this is the complex sign definition, so in the end I would like to go for the Euler's formula, of course, because from there you can get the complex definition for sign. At the same time, Euler's identity is a great explanation of... Well, it's a great demonstration of how imaginary numbers can be used to describe rotation. So... And then the cosine and sine there. Okay, I think I have a pretty good idea how to do it. And yeah, looks like this. Function... You have a function. This definition. Then you simplify. Take the derivative. After taking the derivative, you realize that it's zero, which means that this function isn't changing, which means that left side is equal to right side, correct? Am I thinking about this? Constant, yeah. Hold on, my brain isn't braining at the moment. Yeah, the derivative of 0 means not changing, so it's constant. And since we know that f of 0 is equal to 1, then everything must be 1 because it's constant. And so, if everything, right, if this must be always equal to 1, then this must be always equal to... Okay, so the top always has to be equal to the bottom. Alright, simple. It's equal to 0, which means that it's not changing, constant. And so, since the function at 0 is equal to 1, it being constant means it's always equal to 1. And so if we go back to the original equation, original function, if this is always equal to 1, then the top of the fraction bottom, which means e to the power I theta is equal to cos theta plus I sine theta. Yes, that's the basic idea. And from here we can go. Actually, you know what? This is just beautiful. I've gotta say, this really is quite beautiful. So yeah, let's go this way. Sin theta. Now, why would that be useful? Perfectly reasonable question. Well, if we go back a second, we might point on it, going around. You can see that. So we move it around. If we use the sine function to represent the x coordinate and the cosine to represent the y coordinate. How is the animation doing? Speaking of, just wondering. Still going. Sweet. Makes sense. I didn't stop it. That would make sense for it to keep going. Cosine represent the y coordinate. Then no, cosine the x-coordinate. Ah, I screwed up. Cosine function to represent the x-coordinate and sine function and sine to represent the y-coordinate. Then we get a rotating point. Which means that cosine of theta point going like this. Sine of theta would give us a point going like this. Times an imaginary number. Complex plane. If we add both of them together, it might have been a mistake to want to end this with a Fourier transform, I'll be honest, because that's, to be fair, that's the only way to tie in everything nicely. Like, yeah, with the Euler's identity, you do need the trigonometric functions, you do need the complex plane, you do need the derivatives, you don't need the integrals. So, I guess. Point going around a circle based on theta. And wouldn't you know it, it just so happens that this is equal to e to the power of I theta, correct? Theta, right? This formula. So e to the power of I theta gives us units of, okay, based on the rotation, right? Coordinates for the real plane and coordinates if not plane, axis and coordinates on the imaginary axis of this point based on the angle provided. There we go. And so, we've ended up with a simple function. I mean, it's truly simple if you consider e to the power of I theta. Considering how simple it is, incredible. Simple function, which describes rotation perfectly. Number. And right here we're gonna need a recap, because, oh my goodness, it's a lot of information. And also probably like an example of where this could be useful. Yes. Like a polar coordinates thing. That would be, oh, that's a pretty good one. But what kind of polar coordinate? It's polar and Cartesian, correct? Cartesian coordinates? Oh my goodness, I can't spell this, there's no way. Cartesian, it's a single E. Oh, it was a simple spell, damn it! Unique by a pair of real numbers, that's important! I already mentioned it in the past. And right here we're actually using complex plane as it doesn't matter. The point is, that making the corners really fire. The point I'm trying to make here is, so, and all has happened. This recap. Oh, I should also end it with a pan like, yeah, that's enough of the recap because I don't want us to keep going in circles. Because more coffee, we'd love some. I'm fine, I'm fine, I'm fine, I'm fine, I'm fine. Oh, actually, both my arms snap. That's ouch. Okay, that's happened. So let's recap. Actually, where would I recap? No, the recap is pointless. I skipped over the entire proof and everything specifically so I won't have to go over it, so going over it again would be kind of pointless. Hold on, let me check something real quick. Give me a second. Oh, never mind. All good. Such an incredible build-up, such a like a mid-song. What's happened? Yes, that's... if indeed. That's a good question. How am I supposed to recap this? I haven't given enough information as it is. A minute? Why a minute? You can't see it. There we go. It says a minute. It takes a minute. It took a minute to render a single frame. Why? What were you rendering? I mean, there is a volume, but it's not. It shouldn't be done then. Okay. Damn it, I'm kind of stuck on this. It's fine. I'm clever. I can figure it out. I did. take an angle. I got this right, correct? Yes, okay, cool. Yeah, cosine is real. The real axis. No, before this we need another question. Why is sine multiplied by I? Hi, the Kuan. Hi, welcome. Hi, how you doing? I'm good. Glad to hear. Yeah, it's good. Solid. Okay. Bruno skipped over. Struggling to make one specific node I have to teach this Friday. You have to wait, you're struggling to make the node you have to teach. I see. What's the knot? Monkey's Fist. That's such an odd name. Monkey's Fist knot. Oh, it's this one! Oh, I see. Okay. Oh, yeah. Oh, that's Monkey's Fist. I have a friend who's really good at making them. The trick is to go slow. Really, really slow. And also you really don't want to screw up on the first ones. Like on the second try, when you going across is so much easier than going to the side. You know, when you're switching from the front to the side, the hard part is tightening it. Well, for you, yeah. How are you tightening it? Are you tightening it at the very end, or when you're done with each side? I missed all of that. Oh, yeah, I was just asking. I was asking if you're tightening it at the very end, or when you're done with each side. At the end. Oh, I see. You have to tighten it at each side, but only with the second and third. So you start the first side, you don't tighten it much because the base, and then the second one and the third one you tighten when you're done with them. And then at the end, when you're gonna tighten the whole thing, it's just gonna fall into place much more nicely. Oh, back. Hi there, Sahid. Hi there, Skitiyad. Hi. You're welcome. Feynman's first lecture. How was it? We're getting a video of complex numbers. Well, we're getting a video of math. Chapter number... What's chapter is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 12th chapter. Well, the 11th chapter is all complex numbers. So... it's kind of all complex numbers, I suppose. Computer science, huh? Oh, I'm familiar with this one. Delicious. Why is it taking a minute to render a single frame? That's ridiculous. A minute? What am I rendering? I know it looks nice, but there is nothing... Is there anything? Well, the volume's there. That's it. There's only... The volume is the only thing I can think of that would take this much time to render. The word? No, that doesn't make much sense. What is taking up all that time? A minute? It's a ridiculous amount of time. Unless the light balances are for some reason way off. That could be it. I'll have to check after it's finished. Which point is, and then the distance from the origin. No. That's... Yeah, I just realized I haven't re-mentioned vectors. That makes sense, to be fair. Videos are kind of tight. I will probably make a sequel to this video. Probably. Because I would really like to make a similar thing for linear algebra. I just don't know where I would go with it, to be honest. Because like right here we have the Fourier transform, which really nicely, in a beautiful way, ties everything together. But when it comes to linear algebra, I can't really think of anything. So yeah, I don't know. I will probably make a video, I just need to find something. It's vector. How do you do your research? Slowly, most of the time. I on stream really often too. I know exactly what's the answer you're looking for. I use Wikipedia for like to look up something real quick because it has articles and everything, and for more in-depth about the topic, I use LibreText. My beloved. I have this textbook bookmarked. So this is, for example, the textbook I used to make the addition to quantum mechanics video. Okay. Vectors. So for the Cartesian, we use vectors. Polar, however, we use, if I'm not mistaken, it's r times e to the I theta, if I do remember correctly. That would make sense, certainly. Yes. Right? Yes. Right. Yes? Right. Yes. Right. Yeah. No. Yeah. Yes. No. Hold on. Can you really say complex numbers are vectors? No, they're not. They are very much not. Polar, however, Lisa. Yeah. Vectors, I mean, they act and behave like them, but are they? They do not. They have a property which is quite contrary to vectors. You see, when it comes to a vector, if you have x, y, z, w, for example, then x in no way, shape or form can influence w. No matter how you operate on the x, unless you use another thing from linear algebra like a matrix or something, you cannot just simply operate with standard operations on the x and have it affect the w. If you multiply the x by 4, if you bring it to the 7th power, or if you tetrate it to 11th, it will not affect the w. That's pretty important. That's because for example, we have the in our universe, we have 3 spatial dimensions, x, y, z. And the thing is, mathematically, you can also do the maths for the w dimension, but we cannot really influence w dimension because, as I mentioned, these coordinates cannot influence any other one. Now, this is different, however, for imaginary numbers, and that's because when it comes to imaginary numbers, you have x plus iy. And so x can affect the y if the x is negative and you take a square root, for example. Then you're affecting the other coordinate. That's something that cannot really happen. That's why rotations are possible, for example, with e to the I theta, but that's not something you want from Cartesian coordinates. Basically, if you have a completely flat universe, then there is no way for anyone in that universe to move to the 3rd dimension. Drop the walls. Out of context, that would be a pretty weird thing to comment, Quad. Theta. Makes much more sense. Yeah, I mean, for most things, it doesn't really matter all that much because, well, taking a square root of a negative number doesn't really happen all that often, but it still is an issue, which it still makes it mathematically different. Also, then you have quaternions, you can add them to the mix, and then that's way different than 4th-dimensional coordinates. So, once again, how would useful? Well, you have a distance laser and time it took to reflect. Point it at the wall like this. If you know the distance between detector and the light spot and the wall and the reflection point, and if you know, I'm skipping over the fact that it wouldn't work in practice, alright? I'm making a video here, we don't care about realism, it's a hypothetical mathematical, we're doing maths, not physics. And if you know the add, then you can get the exact x and y coordinates point. There we go, that's why it's useful. Right? Am I wrong here? I feel like something doesn't seem quite right. I'm stuttering because I'm thinking and I cannot focus on two different things at the same time. Okay, so you take this. Oh, let me draw it. Screw it. Drawing it. Alright, so a roll like this. We have a device going on. That's alpha. That's R. Then yeah, e to the power of I alpha, for example. That would be a point on a circle with radius 1 around it. And since it would be exactly, its radius 1 is actually 1 distance away, then if we multiply times r, then we just multiply it this way, and so we end up right here. Yes. And then the real part, so the real part of our function would be the x coordinate, and the imaginary part would be the y coordinate. Something seems off. I don't know why something seems off. Nah, I'm certain it's fine. Of the point. Okay, oh my goodness, we scripted, I'm pretty certain that's actually it for the complex sign definition. And so, it has been a journey, but we can finally answer the question of what is sine. Because this identity we can derive equation for complex sine and cosine. There. If you'd like, you can solve it step by step for a number and see that it is in fact sine and cosine. Oh, okay. Sick, nice, neat, fantastic, lovely, festive. Will you be making a channel membership? You mean I should really plug it into more videos, you know, then, because if apparently no one knows. Do you all just skip ad segments? Hold on. I have a Patreon. Quad is a Patreon, in fact. I'm pretty certain. This dropped. Oh, 93 a month. This Quanda, you are a patron, right? You didn't just quit on me, did you? Yes. You are. What? You know how hard I work on the ad segments? Not really. I don't really work hard on them. It's still am. Okay, good. Fee you. Fee you. I'm get to siphon away more money for, but not for long. Consider my heart. I'm heartbroken. Really? To be fair, you have given me a lot of money, so. You have 16 bucks left in your account. It's fine. It's fine. Don't let me guilt you into staying a patron. You gave me a lot of money. You cannot. It's fine. It's fine. I'm just joshing around. I'm jesting, you know. I'm just a kidder. Sine and cosine. How the heck am I going to segue from this to the Fourier transform? I'll be honest, I don't know. Where's the Patreon link? Shouldn't it be? It's on the channel. Hold on. I really should plug it, but why is YouTube like this? They don't like Patreon. They have membership. They much rather I use membership, but I can't really offer anything with the membership. I really can't offer anything with the membership. It's on the side right there as Patreon. Should I do a transform about curves? I mean, Fourier transform. I would really more like to focus on the angle of frequency when it comes to Fourier transform. You know, the whole getting the frequency of waves. You know what, screw it, I'm just gonna do the lazy segue. And so, all that information in mind, we can finally move on to, and then just Fourier transform. Pop this equation on screen and just leave it there. Why is the text so big? 11. There we go. Should I set up a membership on YouTube? I can. I just don't wanna double bill people. I guess. Let me check. How much does YouTube take of memberships? I remember it was a lot. Creators receive 70% of the membership revenue after applicable taxes and fees are deduced. Mate, that's gonna be less than half. Hold on. So you mean to tell me that out of membership I get 0.7, multiply that by 0.7 because the American tax takes 0. I get less than half! What the heck? I genuinely, if someone donates $1 through a membership, I'm gonna get less than half $1 for it. Add the Patreon link in the description. Is it on the description? Did I delete? Oh yeah, because it's a charity live stream. I didn't want people to donate on Patreon. That's why. Okay, that makes sense. I can add it in the description. But that's just robbery. That's just thieving in the dead of night. $41, 49%. Really? Patreon. It's gonna be patreon.com/sub to make it, correct? Aha, there we go. I remember my old nickname. Oh, sweet. There we go. It's in the description. 49 cents on $1. That's ridiculous. Okay, doesn't matter. Fourier transform. Fourier transform is going to be a bit more of a tricky one. Well, first of all, it's a transform, not a function, so I have to explain that. But I did explain integrals, I did explain the functions, I did explain the complex, it's not really a complex sign definition. I called it a complex sign definition, not really, it's complex rotations. I did explain the complex rotations. Actually, this is more about oscillations than it, less than rotations. Complex trigonometry. Yeah, you know what, first of all, we could focus on the animations. Nice little yet to do. Inverse operations, right. Just okay. Increase the side, decrease the side. That's simple enough. Just take this, and then right here, 1800s. 60, 1800. Oh, we don't want to wait too long. That should be 2 seconds, because it should be 60. No, 48 will be 2 seconds. So let's do 1838. I'm really trying to save time on this, because, well, we don't have much of it at this point. I hate how this is off-center for some reason. I really screwed up bad, didn't I? That's awful. That's awful looking. I mean, the reason why it's off-center, if I'm not mistaken, is because I moved the rectangle, I think. I think that's why. Still. I'm gonna... You know, I have to fix it. I can't live with it like this. Unfortunately, I already rendered the previous animation, so I'm gonna fix it in a bit of a cheesy way. But basically, this is the... coordinates of the text in the center, if I'm not mistaken, which means we copy it and we work with this one. There we go. Did we add the wrong thing? Oh, I think I just... Wait, is that a flat... Am I just adding an arbitrary number? Oh, no way, I screwed up this. I did. I absolutely did. And we're just adding an arbitrary number, and I just misplaced it. Make it, that's such a dumb solution. Oh no, we're not adding an arbitrary number, are we? We're adding this. We're adding the... Oh, that's... Make it, you bloody idiot. Oh, I'm such a... It's fine. It's fine. It is fine. What happens if we do negative 630 there? No, just leave it like this. There we go. Get a little bit more to the left. Okay. There, now it's in the middle. Now it's in the middle. And now, we will need a mix vector. Because of the simplest one, I could do it with multiplications, but what's the point if I would just make my life more difficult? And now we can just move it. Like this. And it's in the center. How sweet. Festive. Neat. Cool. Now I have to just wait for it to render again. Okay. Next, then... I mean, after this we have functions, which... That's actually a surprisingly short chapter. That's good. Oh, I could record the whole video. Or I could just script the Fourier transform segment. That's why I like Wikipedia so much. It just gives you an article with all of the surface level knowledge you need, which is just great. I know what Fourier transforms are, I just need the maths, because I don't have it memorized. I'm not a mathematician, I'm a generalist. I've recently been making a few too many physics videos. Okay. Not definition exactly. Wait, am I looking for a definition? Yeah. Yeah, and discussion about exactly the image process which creates the... Why don't you use ChatGPT or something like that? Because it can lie. I don't trust it enough. ChatGPT hallucinates a bit too much for my liking. The biggest issue is not really the fact that it hallucinates, only that you don't know when it's gonna hallucinate. So I could just confidently say something completely wrong in the video, and then not catch it. So unfortunately, I cannot. Analogy. No, I know it does. I need the maths. Shows how harmonic frequencies something is given by the analysis formula. Yep. That's not exactly helpful. Not quite what I'm looking for. Nope. You could transform from complex sign to Fourier transform. Yeah, but then what's the point of me in there? It's a slippery slope. At one point I could just ask ChatGPT to script a video for me, and it's not gonna be great. Listen, the thing is, I could use ChatGPT, but so could everyone else. Why would anyone watch my videos then? I do have the animations, but I really want to make it kick to it, you know? The thing is, what takes up the most time for the video making process isn't scripting the video. It's rendering the video. So if I'm waiting for this animation to render, it's not really worth the time saving, you know? It's not gonna save me any time anyway. This includes me. Yeah, okay. Not quite. You know what? Screw it. Let's do library text. Tenth chapter. Oh, that's gonna be fun. Okay. Hee 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 ha. A function is defined as this. Yup. Just quick click in the background every time you render somehow. See how far you get. I already did that for the electricity video. I could do it again. Cookie clicker. Alright, good. The thing is, in the cookie clicker, you do need to click a bit to get something, you know. There we go. I did that in the past too, but then everyone called it the brain rot stream, and I don't like it. I don't want to be the brain rot streamer. Okay, no, this is not really useful. Trigonometric series, maybe. Could be it. This in last section we are interested in finding representation function to sine and cosine given function. Is representation in form. Okay. Opted to drop a reference in the time frequency of phase. There's some discussion of now. Two representation equation is called the Fourier trigonometric series. Requires in 350 hours. Section of periodic. Does the large period T? No, addicted to streaming. No, I'm fine. I could quit whenever I want. I could quit whenever. I just don't wanna. Finally playing Cookie. What do you mean finally? I haven't been playing it in the past. Oh, how nicely it fits with the Make It actually. I really like it. Look like I'm blowing up Cookie Clicker. Copies of the original. Okay. I know what it does. I just don't. What I want is the definition. I mean, not definition, only the explanation for the definition. I could also figure it out myself, I suppose. I think he'll know when he'll be addicted. The fire's a bit too blurry. And that's actually on purpose. You see, the fire isn't great, I'll be honest. For some reason I really screwed up. I feel like the force might have been too great on the fire. And so I just added depth of field to it. I think he was addicted at 10 years. Oh, we're 1/6 of the way to 10 years actually. Huh. Isn't that fun? We're 1/6 of the way there. Custom Make It promos are Patreon only. Yes, they are. Come on, you're a patron, you should know that. Also, you have requested Make It's on... You've requested like 5 Make It's at this point. Where's the Patreon only? I'm giving now. Yeah, so what? Still Patreon. Okay, so right here we have the Fourier transform. Now, this takes in the function e to the negative I 2 pi epsilon, I think that's epsilon. Do I still count? Yes. It's any patron. But in the first parentheses, I recognize it. I think it's epsilon. I think, let's see. Never mind. No, wait, isn't this? No. Rho? No, not capital Rho. What's the one starting with Z? Zeta? Capital Zeta? No. I don't know actually. I'll be honest, I don't. Oh, I misspelled. Wait, did I misspell it? Is that the right one? I did misspell it. It was G, she, whatever. I can't pronounce it. Couldn't even if I tried. Okay, so we start with the function. This take an integral of it from negative infinity to positive infinity. So this is the key part, correct? Obviously, this is what makes. Okay, I think that's it. I've gotten dragon egg and cookie clicker. Yes, I have. And then the dragon, the golden cookie dragon. That's probably my favorite golden cookie you can get. It's just great. And the element variable x represents time within the YT. Variable. Kuan, calm down. But it can also be written in terms of angular frequency. But okay, so this is just oh my goodness. All right, let's first reverse engineer this, just for the sake of, just for the funsies, you know. So this can also be thought of as this if no, I'm just gonna if omega is equal to 2 pi there we go. So that's the transform variable, which represents frequency. If time is measured in seconds, then frequency is hertz. For transform can also be written in terms of angular frequency. That would be, so omega is angular frequency, g is the frequency. Okay. Radians per second. So yeah, so we do probably care more about radians because that's where we're going. This, well, do we care more about radians? No, that's angular. I'm an idiot. Yeah, I don't know. I guess this is wrong. Conversion. So we don't care about angular frequency actually. Extension of the definition. Maybe history, complex sinusoids. Yeah, that's Euler's. Ooh, but that's multiple. Oh, okay, maybe something there. Simplify using the product form. How easily a real form was deduced by an application of Euler's formula. Yes, that's true. Oh, so okay, rectangular coordinate. I guess rectangular makes more sense than Cartesian. Caleb, you mind not pasting in the LaTeX, like, brackets if you want to paste in the question? Jeez, that's unreadable. Okay. U squared minus ut is equal to 6. T squared minus ut is negative 2. Then 2ut squared. That's u squared minus ut. I guess 2 should be enough. Will you let me solve it? I can. Alright. U squared minus ut 6. T squared minus ut equals negative 2. 2u minus t. Why am I a genius if I solve it? Doesn't. Yo, is that one of them difficult questions? I don't want to solve it then. Minus, right? Yes, minus 2ut plus t squared, if I'm not mistaken. I do believe. It's times 2, so 2u squared minus 4ut plus t squared. And I couldn't help but notice that right here Caleb, where did you get this question from? You silly goose. It is. Oh wait, but it's 2, isn't it? Oh, I see. Never mind. Never mind. It's. Oh wait, this is also 2. Never mind. So this. So sick. So in other words, this right here is 2 times 6 minus 2. Yeah. Am I wrong? Apparently, it is 8. That's such an... I thought it was something... Honestly, when I saw UNT, I thought it was like an integration question. I wasn't expecting it to just be maths. Basic algebra. Where'd you get this question? If you solve it, you're a genius. Threw me off. I thought that you copied like a, 100-year-old unsolved question posed by Einstein or something to get. But yeah. Set this study. I know how to do it. Oh, I see. Oh well, then I can help you out with this actually. The way you do it is. Oh, that's the wrong paint. The way you do it is, well, you first turn to this, right? And then you can see that if you take both of these together, then right here you have u squared, 1, 2 ut in the negative, and then t squared. Which means this will be equal to this plus this, or in other words, 6 plus minus 2. So 8. Hope that helps. Got the cookies to click. So this has 3 forms. Alright, so we do it this way, and then 2 pi. Yeah, it's a new one. I just made it. There we go. 2 easy achievements. Now, pull a coordinate form like this, e to the... So the reason why g is in there is because 2 pi, that makes sense. It's the radians conversion, right? Yes. What type of batteries or power source did you use for electronics project? A power supply, just a DC power supply. Come on, chill. It's just a knot. You should not worry. Am I an idiot? I must be an idiot. I must be an idiot. The output of the transform is a complex valued function of frequency. Yes. Okay. Time was twisting on the rope. Past 4 years. Oh yeah, I get that. Oof. I hate those. No, you don't have to unknot it, it's like a bend. If you get a rope wet, tighten a knot, and then I didn't clean the glue and cooking time. If you get the rope wet, tighten a knot, and then get it to dry up, then when you unknot it, it's like it's so awful. The chapters actually complicate the main properties for the transfer example. That sounds useful. No, I know the example. No, that's not the example I was looking for. I know why in my brain I thought it was going to be an example of how to understand the. I don't know how to, you know, like step by step get it. Doesn't matter. The point is, so this is the definition, which. Speakers to infinity when your abilities are continued. Okay. So we need to understand the Fourier series in order to understand this. That would make sense. So it's just like a continuum Fourier. Okay, Fourier series. Sweet. Real functions and trigonometric functions. Okay. Right. So why Fourier series? Okay. No. Is there like a... It's just history. No, I'm looking for more like... No. Okay, so... I just need to figure it out for myself. Got it. That was an outstanding animation, actually. Huh. But wouldn't be the analysis, the synthesis? Wait, synthesis or Fourier transform is an analysis product decomposing for. Okay. Well, yeah, wouldn't that animation be about synthesis? Oh, these are all just like killer graphics, I gotta say. This is outstanding. My entire job is just about making graphics. This is just about as good as it gets. It's really great. Okay, so you sum together. Makes sense. Now the only question I have is, why the heck? Well, first of all, the one question I have is, was the actual equation? Because it's not quite here. I mean, there are forms of it, which I don't know if form is what I'm looking for. Amplitude phase form. I don't know if that's what I'm looking for. But if that's the way how Fourier transform, well, no, Fourier transform, no, because that was clearly synthesis. We're looking for analysis. So we want the opposite. Well, it doesn't help much, does it? Because infinity, you can forget this out. So we take the function. Why do we multiply by this? That's in the okay. That's complex, right? No. Yes. No. Yes. Yes. No. Yes. It is complex. No. Yeah. No. Yes. Screw it. I need a textbook. When's the Fourier series? That's a wild question to ask. Trigonometric series. Yeah. Yeah. That could shed some significant light on the situation. So it's got a function of secret presentation in the form of yes, great. Of face. Okay. The series application equation is called Fourier trigonometric series. We'll simplify for coefficient. The competition is simpler. Having found the Fourier series representation, we will be interested in determining when the Fourier series converges and to what function it converges. Makes sense? Yes. From our discussion in the last section, we see that infinite series is periodic. Largest period of this terms comes from n equals 1 terms. The period of the terms comes from n equals 1 terms. The period of cosine sine of, as the Fourier series has period 2 pi, which means the series should be able to represent functions that are periodic of period 2 pi. Okay. Together, the expression representation of the origin, therefore we will first consider Fourier representation of function defined as interval. It's easy to consider function defined. Okay, so I'm sorry, what? The Fourier series. Oh wait, go on, cookie. That's nice. So the Fourier series representation of fx defined on 2 pi is given by equation this. Okay, so you just start with the okay. I'm not upset. Alright, so let's make sense of this step by step. We're just slowly dissecting the issue here. Also, how's the animation doing? For the sake of satisfying my curiosity. It's still rendering. Sweet, fantastic, lovely. Okay, so this is f of x cosine nx dx. Okay, makes sense. Is that cosine of nx or cosine of x? So I think it's cosine of nx. That would make sense. And thus, x is obviously there because the cosine. Right. Oh, but we're integrating over the x. Okay, so this is one render for now. Yeah, because if I set up more than one, then it actually slows down the other renders, and it doesn't actually give me all much time. This is given by equation 521 with 4 coefficients, which are and a n is equal to 1 divided by pi and 0 to 2 pi. Okay, so we have a function which we multiply by the cosine, and then we take that function, we take the sum. Alright, so we take Desmos, like so. And we have a function, f of x, and something like, I don't know, freaking sine of 7x, whatever. And then what we have is we have this, which is f of x times cosine of nx. And we define the n as, so we have 1. Let's have it go from 0 to 100 with a step of 1. Oh, that's really quick. Okay. Oh! That makes sense. We're multiplying two waves. Okay. That checks out, yeah. So what happens when we take the integral of it from negative infinity to positive infinity? Not from positive to... Oh no, from 0 to 2 pi. Right, so what we care about here is 0 is smaller than x, which is smaller than 2 pi. This is what we care about. Okay. We take the integral of this, of the blue one. Maybe multiplying it by an integer doesn't have a 7-2. Okay. Sweet. And 100 might be also a bit much. Let's do 10. Let's go. I know, it is cool, but let's now take this and let's have an integral from 0 to 2 pi of dx. And let's have, just to visualize a bit. Oh, because it's x, isn't it? So let's do t. Whatever. T is fine. Okay, so we can see that as it gets... it converges on something. Alright. No, wait, it doesn't. Oh, as it gets closer to 7. Okay, sweet. As it gets closer to 7, it spikes. That's cool. Now, that's really cool. As it gets closer to 7, it spikes. Now, why does it spike at 7? Oh my goodness, okay. I'm getting there. Because 7 is close to 2 pi. No, I mean like, why does it spike at 7? I know that's why, right? Yes, that is why it spikes at 7. But what we're asking here is, why does this actually give us the answer? And the reason appears to be... no idea. Okay, so 7... if we had that at exactly 7... then this is actually 0. Huh. Okay. Everything is 0. If we have that 7. Okay, so we have that at an integer. Okay, so let's do 7.1. And so then it spikes at 7. Okay. Okay. Spike at 7. And that's because if you take 7, if we input it here, then we multiply, then we basically just have the function. No, it's cosine. That's because I'm an idiot. We have a cosine and a sine. That's why we... Oh, that's why in the Fourier transform there's e to the power... Okay. Right. I think I'm getting there. I think. But we do care about cosine, not the sine, correct? Even though we're doing a sine. Okay, if we have a sine, it fits even better, but it works with cosine too, so we're gonna go with cosine. If we take the cosine, at 7, it's really similar. Why is it really similar? Well, it's because what we basically end up here with is sine of 7.1 times x and cosine of 7 times x. So if we take both of them together, what happens if we multiply sine by cosine of the similar frequency? Well, if we take a sine of 3x and multiply it by cosine of 3x, we get it just below it. Oh, it's staying flat. Okay, so that's the property we're looking for, clearly. It ends up being... Okay, so it ends up as a... Okay. Okay! When we have the sine and cosine of the same frequency, multiply them both together, we get a wave. Makes sense? It does. It really does. But why did that result in a higher number? Because it's more slowly rising up and then... Okay. I think I got it. I think. Gee whiz. Alright. So... if we were to make like a bit more of a Fourier transform, then this would be negative infinity. This would be... we'd turn this off. This would be infinity. Like this. And so now... that we have that, it would just fire off to infinity. Never mind. At 4, it's practically equal to 0. Okay, sweet. Ha ha ha. We need an actual number. So it's undefined for everything except 4. Ha. It's okay. It's okay, whatever, yeah. Is it because it's... oh, it's because it's oscillating. Never mind. That makes sense. That makes sense. Alright. What happens if we multiply it? But no, this won't work. Why is it equal to... why is it 0 at 4? What if we do this? Whoa! I am just having... but I could just check it online, I suppose, but then I would just be stealing answers. What's the fun in that? How's the animation doing, by the way? It's doing well. Okay, good. So, going back to the Fourier transform. If we pick a frequency right here, which just happens to align pretty well with our equation, what we're gonna get is just like a cleaner wave. Then the features are gonna become more pronounced. But why the integral from negative infinity to infinity would do anything? As you got the camera crack your face or something. Cool. I mean, I suppose. I'm very stiff in real life, you know, I just move in two different ways, that's it. My brain is hurting. It's fine, I can figure this out. So, we take this. Why the integral? No, this is driving me nuts at this point. If I have a cosine, yeah, the frequency don't do nothing. What if? No, I can't. The problem is I can't plot things with imaginary numbers in Desmos. Desmos cannot handle imaginary numbers, as far as I'm aware. Maybe it can't somehow, but no. I'm struggling. So this, at the end of the day, is Euler's not identity on the Euler's formula. Euler's formula. Right. Euler's formula is useful because it can give us an angle. So why would the angle matter? It wouldn't. It wouldn't matter, you see. Funny enough. It wouldn't. Why would it matter? It wouldn't. So, formula right here, this, but we also have a negative in there, just to mess with me. I'm not struggling. I'm just tired. I am finding out more and more stuff, but still doesn't help nearly enough. Fourier series, I suppose, that should explain it, shouldn't it? Period of 2L conversion Fourier series into form. Periodic function f of x with a period of 2L can be represented form of this. A0 divided by 2 plus this. So an infinite amount of... Yeah, see, this would make sense. That's because this could be... But why the I negative 1? The... Okay, so... Okay. And have a cosine. And we end up with this absolute monster of an equation, alright. What then? First integral is 2L. Ah. Ah. N is equal to 0, 1, 2. First, second integrals on the right hand side are 0. Third integral is Okay, so first and second right side are 0. That makes sense. The first one makes sense. Oh wait, the first one. I mean, this one makes sense as 0. I think. Provided previously. 1, 2, 3. We get this. If you say so. Oh, my head hurts so much. Did it finish rendering? No? Okay, I missaw them. Oops. My brain is hurting a bunch. So 6, 5, and 1 was it? Okay. As Fourier series in the form. So we have a Fourier series. Which... Okay. Zero divided by 2, that makes sense. A0 is there. No, it doesn't. No, it does make sense. A0 is there because if n is... Because otherwise we could just start at 0 right here. And if we start at 0 right here, this would be cosine of 0 always. And this would be sine of 0 always. Be a constant. Okay. Sweet. Now what is the A? Coefficients. Makes relative relations for sine and cosine. Okay, so yeah. Alright. One is in the m and otherwise it's just 0. Okay. Which means that first define the wildly used Kronecker delta. Is it now? Is it wildly used? And coefficient A of n, multiply both sides of 931 by cosine of this. So we take this, multiply both sides by cosine. Aight. Non-negative integer, and change the dummy summation variable from n to m. Integrating over x from negative L to L, assuming that the integration can be done term by term, in the infinite sum, we obtain this. Makes sense, we multiplied both sides by cosine and then we integrated. Okay. Okay. I mean, okay. If n is equal to 0, why would n be equal to 0? Wait, what is n? No, n is the... So we take this, we have n. N is the... Oh... It's this n. Okay, so it's just... Okay, so if 0, then the second and third integrals on the right side are 0. And the first integral is 2L. Okay. N is a positive integer, then the first and third integrals are 0, and the second integral is L this. Okay, so we have this. Summation extended as 0, Kronecker delta. Therefore we obtain n for n 0, 1, 2, and so on. This. Buddy, I'm really struggling. The first time math isn't easy for me. Get in line. Get in line. Okay. Summation except 0 by the virtual Kronecker delta. We therefore obtained n 0, 1, 2. This. So right here, okay, the reason why this is nice is because this doesn't actually have imaginary numbers, which means we can dissect it in Desmos to at least try to figure it out. So, 1 divided by L, an integral from negative L to L. Actually, maybe it should be X, that would be better. You know what, let's do H of L is equal to this, dx, f of x, cosine of n divided by L, and that's pi n pi x. And then what we do is right here we do h of x. Okay, what did that do? This is... Oh, we have the n which we need to vary up. Oh, I see. Do we now? Okay. It's integers only, so... And that determines the an, which is right here, the cosine part. But you have a sine, so if we change it up to a cosine, will it do anything? This is cosine. This is a cosine. There. Now, how about... Why did it freeze? Why did Desmos freeze? Oh no! Oh no 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 no! There we go! Oh! Witchcraft! I get it now! I mean, I don't. It's okay. Let me be clear about what I get. The Euler's formula is there to come for sine and cosine. And based on this, we should be able... Our line is to now collect the 7 trillion dots and then congrats. Like 1/3 of the way there. Uh-huh. What happens if we change it up to 13? What then? This one is really slow. This one. Not every day that you get a laggy in Desmos, actually. I suppose it must be all of the integrals. Okay, so what's happening right now is we're taking the... Okay, I can figure this out. I'm a smart boy. We're doing it in... So this is what's happening for all the L's. So right here, we have... We're getting the cosine. N pi x. Oh, we can remove the pi. That would clear it up, actually. Because now we have cosine. Every the viewers see. I'm walking something. Okay? So we have a cosine. We have a cosine of nx, which listen, I get that the pi is important there, but I'm trying to think of the most. It's so cosine of n. So when you get to 13, it's basically we divide by L. Integrating with the L. Oh, when we get to the peak. Oh. Oh, I think I get it. Oh my goodness, did I just get it now? Oh, please tell me I got it right. So, we integrate from negative L to positive L, which means if we have like a... Paint. No, paint. Which means if we have like a freaking wave, right? You have like a wave like this. Beautiful, make it. How about we start in the middle and then go to the sides, huh? If we have a wave like this, then the highest number we can get... I think what's right. Wait, first of all, this is not the way. I'm an idiot. This way, of course. Bonus and negative. Have one like this. Then as we integrate, when L is equal to this distance, we're gonna get the highest value, which is then going to repeat but then it's gonna repeat right here, isn't it? Oh. Oh, but we divide cosine by L. Okay. Right. So... means what we want is we'll take this cosine and see what happens to it. Like a 1 divided by x. Yeah, so as we go on, but the approach is 1, that makes less sense. The divide by L is really screwing with me. Oh, but we divide by L on the beginning, which means as it goes to... Okay, yes, which means the highest value we can get is not going to be right here because we divide by L. Okay, I have no idea why we're dividing by L inside the cosine, but what I do know is right here we're going to get the highest value when L is equal to this. Which means that we get the highest value at negative 12. Okay, alright. What if we're doing all maths wrong because we're using the wrong number system or something? That's... yeah, there's different kinds of maths, you know. So, if we're doing maths wrong... There are like no formal rules about how math is created. If we're doing math wrong, someone at some point is going to make up their own math, which is going to be correct. Like, imaginary numbers we thought of like as a crazy idea, but then they just became a standard, so... Take this, that's 312. I'm getting 312. Okay. Is that how close to this to pi? Why would that be? So we take the cosines, apply them together, increase the L. These are both equal, then... Now I need to... Oh, there are so many variables there. Okay, so... when this is L, that's when it's the greatest number. Also, as we have the cosine of n... As we have this change... Alright, let me just, for a second, remove the h. I'm just adding this with the n. No, we already have the n. So the L doesn't make sense. No, it doesn't make sense. Doesn't matter. So as we have the n increase, we then want to multiply it by f of x, like this. So as we increase it, let's say. Okay, yeah, it tends more and more to the curve. As it tends more and more into the curve, all the negatives will cancel out the positives. But at 13, when does it fit the most? No, never fits the most. It's n pi x. What happens if we were just to have nx? But then it's practically flat, I see. I keep trying to force it in there instead of just letting it flow. That might be the problem. I might be the problem. Oh. Once again, this is not. My brain is not doing well with this. Yeah, you know what? I mean, clearly no one cares about it. I feel like I should do this off stream instead of doing it on stream and boring everyone. I hurt so much. I'm gonna finish this off stream instead of doing it on stream, because clearly no one wants to see this. And I get it, I'll be honest, I get it. So, for now, I suppose that'll be it. Thank you everyone so much for watching, and have a great day. Bye.